We're going to review the mathematics and the process of creating an input-output model. Now, the review that we're going to do is going to be very simple. We're going to look at a basic 2 or a 3 industry type of system. And then later on, we'll look at a little bit more complicated configuration. Now, in review, in input-output parlance, we think in terms of industries interacting with one another. In this graphic here, we have industries A, B, and C, and it would go on for as many industries as we have. And we also have other actors in our economy. Industries A, B, and C are buying goods and services from industries in the rows A, B, and C who are selling goods and services to these different industries. And so what we get in an input-output tabulation is the sum of all purchases that industries make from one another and the sum of all sales that industries make to one another within our industrial structure or the region that we're interested in measuring. And the hallmark of an input-output system, and the part of this that makes it work for us, is that the sum of inputs for any industry, A, B, C, or so on, equals the sum of outputs in those very same industries. So industry A's inputs would equal industry A's output. So if this was agriculture, all of the purchases that agriculture made in my economy, let's say it's the Iowa economy, the sum of those inputs equals the sum of all of agricultural's outputs as it makes sales to industries in my economy, to households, or perhaps export sales outside of the region. This slide illustrates these transactions for Iowa. This is an old slide for the state of Iowa, maybe 2005 economy. Might even be older than that. But let's look right here. Here we have agriculture as column headings, wholesale purchases, mining, construction, manufacturing, retail trade, transportation, and so on. You see how it's organized. And then going down this way, we also have the very same industry. The rows and the columns are exactly the same in terms of the industries that we have. These industries are buying. These industries on the row side are selling. So let's look at agriculture. Agriculture in Iowa in that year bought, and these values are in millions, $1.74 billion worth of inputs from agriculture. Agriculture bought lots of wholesale goods. Importantly, agriculture bought a very large amount of manufactured goods. Nearly everything that you require for agriculture, whether it's fences or tractors or trucks or combines or ropes or pens, everything is manufactured in one form or another. So they have large amount of purchases from manufacturing. They buy a lot of real estate. Well, they're not buying real estate. What they're buying is a real estate service. So if they're renting land, they're making a payment to real estate. Professional services like accountants. Of course, they have to pay workers. In this case, it's $652 million. They pay themselves. In this case, it's $3.7 billion. And then there's other payments that they have to make when they make their agricultural products, all the way down to imports of foreign goods as well as imports of goods for agriculture from someplace outside of Iowa. Now, we can see where agriculture is selling to the rest of the economy in Iowa. Ag sells to itself. We've already talked about that. It doesn't sell hardly anything to wholesale or mining or realistically to construction. If you've ever watched modern construction, you'll notice that they grind up or shred bales after they do work on the medians or in the ditches. And so maybe that's the kind of agricultural products construction might buy. $5.07 billion worth of agricultural sales went to manufacturing. That's because manufacturing in Iowa processes a lot of agricultural products, either into grain products or cereal products or into processed meat products or ethanol. Let's look at manufacturing. Manufacturing, we already know, bought $5.07 billion worth of agricultural inputs, $3.8 billion worth of wholesale inputs. But importantly, manufacturing bought $7.4 billion worth of manufactured inputs. So that helps us understand the intricate relationship between different types of firms. Many manufacturing firms buy and sell to one another in an economy. All manufacturing firms are going to require a heavy amount of transportation inputs to move their products to markets. They are heavy users of utilities. They buy lots of professional services and other types of business services. They make much higher rates of compensation to workers, $12.1 billion. Very few are proprietors, and a lot more of the income, or what we call value added, that's generated in a manufacturing firm finds its way into investors. That's the other property income category. Payments to dividends, interests, or rents. And in total then, you can see that manufacturing in Iowa that year required $77.1 billion worth of inputs. And if you compared that to agriculture, it required $16.8 billion worth of inputs. And if inputs equal outputs, the size of these industries would be exactly the same on the output side as their input side. So we need to start working through the mathematics of compiling an input-output table, the very basic mathematics. So let's begin with this simple summary that all industrial output equals the sum of all inter-industrial transactions plus sales to all final demanders. And final demanders are the last users of the product. They could be households, they could be government services, or they could be sales to exports. So we could write that as an equation where x equals output, y equals final demand, and z equals inputs, or the inter-industrial sales. So x1 for industry 1, output for industry 1 equals the inputs, z11, that's z buying from itself, z12 buying, that industry buying from the other industry, plus all of its sales to final demand. And the industry X2, the second industry, X2, let's say that's manufacturing or something like that, consists of the inputs that it buys from the other industry, 2-1, plus the inputs that it buys from itself, 2-2. Remember, manufacturing bought lots of its inputs from itself, plus Y2, which is the sales to final demand. So for a point in time, all of these relationships are fixed. We're going to take them as an indication of what a phrase I'm going to use later on, our production formula, or the coefficients of our production process. So what we want to do is reduce these input values to coefficients. And the way we do that, let's go up here just a little bit. We take the values that are in each one of these values, these input values, and we divide them by the total. And what that's going to give us is the percentage of output that came from these inputs, or these sales. So we're going to go down here, and I'm just going to represent it here. I'm going to take, for first industry 1, I'm going to take inputs Z11 and inputs Z12, and we're going to divide them by the total output value for industry 1. What we want is a coefficient. And for the second industry, we have Z21 and Z22, and we're going to divide those by X2, the total output value for my second industry. Now, what those will give us then is a simple table of coefficients, and now I'm going to write them in small letters. A11, A12, these are the inputs for the first industry, and A21, these are the input coefficients, and A21 and A22 are the input coefficients for the second industry. Now, these can be extended down and across for as large as our matrix is, but right now we're just talking about a 2 industry. So now we can rewrite our original formula as output for industry 1 equals that coefficient A11 times the output of industry 1 plus the coefficient A12 times the output of industry 2 plus Y1. And we can take X2 is going to be equal to A21, that coefficient, times X1, that first industry, plus A22, that coefficient, times the second industry, plus the final demand, Y2. So we now are getting this into a form that we can start working with algebraically to produce an input-output model. So we're going to process this with matrix algebra where x equals a of x plus y. Now I want you to look back up here. X equals some a of x plus y, where x, my matrix x, equals x1 and x2, that's a matrix, equals a of x. Well, my a's are my coefficient, and this is my table of coefficients, a11, a12, a21, a22, plus y. Again, those are going to be my final demands, y1 and y2. Okay, now what we're doing is we're solving for that where we left off on step 3 just previously. And again, we have x equals a of x plus y. Now we're going to have to get our terms separated out. And so we can get y by itself by moving a of x, or subtracting a of x from both sides. So I get x minus a of x equals y. Now, if you remember your algebra, I have an opportunity on the left side of that equation to take x out of that equation. And that creates an opportunity for us mathematically to create an element that we're going to need for doing our input-output analysis. If you remember your matrix algebra, if you divide a matrix by itself, it's called an identity matrix. And an identity matrix has ones on the diagonals and zeros in all of the other values. So by dividing x, by taking x out of this left-hand term, I end up with this phrase, I minus a times x equals y. So what we end up with is the phrase I minus a times x equals y. And what we want to do is get x by itself. And so to isolate x, we take the inverse of I minus a. And so x equals I minus a inverse times y. Now this ends up being the critical formula that we use. This is what's called the Leontief inverse. And this is the critical formula that is the prerequisite to all input-output analysis. To recap then, when building an input-output model, we need to know all our industrial output, all industrial transactions, and we need y, this vector of final demands. And if we have that information, we can build an input-output model. So let's look at this in practice. Here I have a 3-industry model, a very simple explanation of some industrial system where there's, let's say it's in million, $34.69 million worth of agricultural inputs that are purchased by agriculture. Agriculture buys 5.3 million in manufactured goods, buys 10 million of service goods, makes $34 million, 0.1 of sales to other final payments like value added or sales to imports. And then the total inputs into that sector are 84.56 million. And remember, inputs equal outputs. And so the sum of all outputs for this industry would also be 84.56 million. And we can see here that agriculture sells to agriculture. We already talked about that. It sells to manufacturing in this economy. It sells to services in this economy. And the preponderance of its sales go to final demand. Again, maybe to households or it may be to exports. So this ends up being our initial transactions table. So if you remember what we did before, we divided those original transactions, I'll go up 1, we divide every one of these elements by this value, the total, the input-output value, 84.56. So when I divided 34.69 million by 84.56 million, I end up with a coefficient. This ends up becoming my A matrix. I end up with a coefficient for agriculture. For every dollar's worth of output, or for every dollar's worth of inputs required, agriculture had to buy 41 cents worth of ag products. It had to buy 6.2 cents worth of manufactured products, and it had to buy 12.35 cents worth of service products. The sum of all of their inputs are going to equal 1, but these are the transactions that occurred within our economy. Some of the inputs that they require aren't in my economy because you had to buy them outside of the economy. And so we have the same relationship with manufacturing and services. This ends up being now the production recipe. remembering that what we're trying to do here is to reproduce the elements needed for this formula up here, x equals I minus a inverse times y. So we know that the identity matrix, what we have to create here for a 3 by 3 region, a 3 by 3, 3 industries in the region 3 by 3, is going to have 1s on the diagonals and 0s everywhere else. We just make that matrix. Next, we subtract. We do the I minus A. We take the values in the I matrix and we subtract the values in the A matrix, those coefficients above. And of course, because there are 1s on the diagonals and 0s everywhere else in the identity matrix, the values on the diagonals are going to be positive and all of the other values are going to be negative. Then using matrix algebra, the I minus A matrix is inverted, the I minus A inverse. And we do that using Excel, and it's called minverse. That's the process for inverting a matrix. And it's a very straightforward process. But we invert that matrix. And what that matrix gives us when we do this, and this is the process and the insight that helped Leontief win the Nobel Award for economics, not just being able to do this, but then to be able to apply this in the study of industries, is that it gives us our multiplier, our total requirements required to produce a product. So when we did this for agriculture here, we ended up with a total multiplier. You sum these values, and we got a total multiplier of 2.25. So what this multiplier means is this. For $1 worth of additional final demand sales, let's say it's agriculture selling as an export out of the region, it resulted in a total of $2.25 worth of output production within our region. We had the original dollars worth of agricultural sales, there's that one, and it also stimulated, after all of the transactions churned and churned and churned through the economy, 72 more cents of upstream agricultural activity as we finally produced this dollar's worth of sales. It required 22 cents worth of manufactured activity, again, from all of the transactions and relationships that occurred in the economy. 22 cents worth of agricultural activity occurred. And finally, almost 31 cents worth of service sector. So you can see the elements of the multiplier plus the total multiplier. We have a manufacturing multiplier of 2.122. Again, it says that for every dollar's worth of manufactured sales to final demand required 10 cents worth of additional agricultural production. Here's the original dollar right here, plus almost 68 cents worth of additional manufacturing that was required in this economy to produce that dollar's worth of sales, plus 34 cents or 34.5 cents worth of service activity. Sum those all together and you get a multiplier for manufacturing of 2.12. And for the service sector, it's the same dynamic, but you can see that in the service sector, the multiplier is much lower. Both that within sector multiplier is lower, as well as the relationship to the other sectors is lower. So very quickly, this is what we're going to be working with in upcoming assignments. Here's that Iowa table of transactions that I showed earlier. Now it's in spreadsheet form. You can see that all of agriculture's inputs, in this case, this is $16.78 billion worth of inputs. I'm going to go over to the right, equaled its outputs of $16.78 billion. Similarly, the outputs of manufacturing, $77.133 billion worth of manufactured outputs, equals $77.133 billion worth of manufacturing inputs. So these are the purchases, the inputs into manufacturing. These are the sales by manufacturing to other sectors in the economy. By dividing each one of these elements by the total values down here, we're able to produce the A matrix. X equals I minus A inverse. So here's my A matrix. The values that were divided by the totals are going to be some fraction of 1. I manually create the identity matrix. There's my identity matrix with the 1s on the diagonals. So I have my I have my A up above. Now I do my I minus A matrix. I subtract the A from the I. And remember then, that because the 1s, it's 1s on the I matrix on the diagonals and 0 everywhere else, I'm going to have positive values on the diagonals and negative values everywhere else. And then using a procedure in Excel, I can produce my I minus A matrix inverse. So I invert the I minus A matrix, and I'll just separate this out here, and it produces the total multiplier. The sum of all of these activities right through here, industrial activities through 17, equals this multiplier for agriculture of 1.67. So in that year, Iowa's output multiplier was 1.67. Its manufacturing multiplier was 1.66. Its finance and insurance industry multiplier was 1.67. And professional services like architecture and engineering is 1.78. Now, these are the multipliers then that become the critical elements of any input-output modeling system. And if you can do this, you can build and apply this model to any industrial change or household income change scenario that's in your area.